All right, so welcome to the last week of physics. Yay. Okay, well, at least last week for this quarter. I mean, obviously, you guys are going to continue on and learn about lovely things like electricity and magnetism and optics and modern physics. But but for this quarter, we're in the home stretch. So we got one more chapter to talk about, and it's primarily the second law of thermodynamics. So let's remind ourselves quickly what the other laws were. There was the zeroth law, and the zeroth law, that was the good old thermal equilibrium thing. If two objects are in thermal equilibrium with a third object, then they're also in equilibrium with each other. Okay, yay. That really just means that temperature means something. Okay, temperature actually is a useful descriptor. So then we hit the first law, and the first law talked about the change in energy. And so it said that the change of energy, the internal energy, so this isn't mechanical energy, this is the internal energy of an object. So the energy that's part of all of the molecules and everything that makes it up, that change in energy comes from two places, either from heat added, right? So we can get an increase in energy by adding heat, or by work done. And when work is done by the gas, the object, then it's lost. So we got that formula. It was the change in energy is Q minus W. And we looked at just some ideas behind that last time, looking at like, remember the one thing we did was looking at boiling some water, taking it from water to steam. And we actually saw how much of a change in internal energy happened, which wasn't much, which wasn't much because there was a huge change in work, right? So, gosh, I'm sorry. Clearly have something stuck in my throat. Okay, so we're going to move to the second law of thermodynamics next. Now, to get us there, I need to give you a little bit of terminology. So let me go to the board so I can write this stuff down for you. All right, so first of all, in terms of processes, now we've got a lot of names for them, like we talked about isobaric, isochoric, isovolume, all those kinds of things. But there are a couple other names that, or descriptors that we need to talk about. And the first are reversible versus irreversible. So there are thermodynamic processes that are both, ones that you can reverse and others that you can't. Okay, so a reversible is exactly what it sounds like. It can be undone. You can go the opposite direction and get back to where you started. All right, so this would be an example. An example would be something like, let's say we've got ice that's melting. Okay, so you can have ice that melts, and that's happening because there's heat being put in. You could refreeze that by removing the heat, right, and the exact same amount of heat that you had put in. So that would be an example of a reversible. Okay, one that would be irreversible is, think about this. Take your hands and just rub them back and forth. Right? So what do you feel?
Friction and heat.
Okay, so you feel your hands warming up, right? And so we introduce the heat by rubbing. So we're transferring this mechanical energy, right, kinetic energy in my hands, into thermal energy in my palms. Okay, this is irreversible because I can't take that heat from friction and turn it back into the mechanical energy of my hands going back and forth. So hopefully that kind of makes sense. Reversible versus irreversible. So most of the heat transfer stuff that just comes from like conduction, things being in contact with each other. So, you know, I've got my ice cold root beer in my warm hand. That can be undone, right? Because I'm just putting heat in, but I could remove the heat to cool this back down. But the irreversible tend to have some sort of a energy that's coming from another form. So kinetic energy or
like burning a piece of paper.
Yep, there's another good one. Burning a piece of paper, that's irreversible. You can't unburn it, right? So some are reversible and some are irreversible. It really kind of depends, but just realize that that's what they are. Okay, so we've got reversible and irreversible. And then we also have what we call equilibrium processes. So an equilibrium process, this is one where the system is always in thermodynamic equilibrium. Okay, so reversible ones are equilibrium processes. Okay, now, not technically, right? Like technically, if we're always in thermodynamic equilibrium, then we don't change. You could never get a change in state, right? Because you couldn't have any heat flowing in or out, and you couldn't have work being done and stuff like that. So it turns out that reversible, truly reversible, this is a theoretical, I'm going to call it a dream. It's kind of like when we talked about elastic collisions. There's no such thing as a completely elastic collision. We can get kind of close, but that's a theoretical best case. Same thing with the reversible. Okay, so really, when we talk about reversible, they're like quasi-equilibrium. They're sort of equilibrium. But it's at least a good enough approximation, good enough guess to go with it. Okay, so just some terminology because it's going to come up when we talk about it. All right, so let's talk heat engines. So first thing I want you to realize is that when we talk about a heat engine, this isn't an engine like a motor in a car, okay? A heat engine is just anything that is going to take heat and turn it into work. So a heat engine could be something as simple as a pot of water on the stove. As it heats up, eventually like the top of the pot will start bouncing up and down and rattling. So your pot is acting as a heat engine. You're putting heat into it, and then that heat is getting turned into mechanical energy. All right, so pretty much any kind of a steam steam-driven anything is a heat engine. But basically, we're taking energy and we're turning, or heat, and we're turning it into mechanical energy. All right, so here's the idea of a heat engine. We're going to have what we call a heat reservoir. So it's something that just has heat in it, right? So this could be the hot pot of water. It can be your engine itself. It could be your body, for example, but there's going to be heat. Now, what the engine is going to do is it's going to take some of this heat and it's going to turn it into work. So I'm just going to kind of draw a little arrow over here. And I'm going to label it work. All right. Now, we talk about efficiency. And the efficiency is how much of the heat that we just took out goes into the work. So something that would be 100% efficient would take all of the heat and turn it into work.
That never happens, does it?
Yeah, exactly. But you can imagine, I mean, think about that idea of just the pot on the stove. Some of the heat is going elsewhere, right? Where else are we losing the heat with that specific example?
The surrounding surface.
Yeah, the air around it, the surface that it's on, you know, whatever. There's going to be heat that's lost. So with a heat engine, yes, we've got this, we've got the work being done, but there's also going to be energy that's lost. So let me just go ahead and draw another little arrow that's coming this way. And let's just call this lost. So it's the lost energy. And where it's going to go is to a cold reservoir. So in the example of that pot of water on the stove, the cold reservoir is just the air. It's just the air outside or something like that. All right, so this is what we're really looking at is with a heat engine, we've got this basically, this is the schematic drawing. Okay, so let's see if we can kind of create a little formula for this. When we think of the change in energy from the first law, that change in energy is going to be heat minus work done. So let's actually quantify this. Let's say that the amount of heat that we remove from the reservoir, we're going to call it QH. I'm getting really fancy. It's heat from the hot reservoir. I shouldn't have written heat here. It should be hot. And let's talk about the heat that goes into the cold reservoir as QC. So obviously the difference in those is going to be the amount of work. Okay, so what I'm going to do here is we're going to write this as the work. I'm going to make it the absolute value of QH minus the absolute value of QC. And this way we don't have to worry about, just in case the flow is going the opposite direction or anything, we don't have to worry about sign. Let's just talk magnitude, right? This energy minus that energy is going to equal our work. Okay, so then if we want to talk about the efficiency of this engine, and this is what we call thermal efficiency, because there are different kinds of efficiency, but this is just based on heat. The thermal efficiency, it's going to be the ratio of how much work was done divided by how much energy was taken out of the hot reservoir. Right, so that QH, some of it goes into work and some of it is lost. So we're going to look at this ratio. All right, so you can actually change this if you use the definition of work, right? And so we can find out that this is actually the same as 1 minus the absolute value of QC over QH. And we tend to like this one a little bit better. Maybe not better, but we can use it in different situations. Like if you look at this one, what we really just need to know are what are the heats. We don't have to actually calculate the work. But obviously, if we can calculate the work, then we'd want to use the first one. All right, so basically what's going on here is the 100% efficiency is going to be a theoretical best, but in reality, we see that that doesn't really happen all that much. So let me show you an example. Let's actually run the numbers on something so you can see how this plays out, because it's not that big of a deal. It's just a matter of calculating the different heats. All right, so for example, let's say we've got a truck, and what we know is that this truck uses, let's say, 20,000 joules of heat, 20,000 joules of heat to get 5,000 joules of work. Okay, so we're going to answer some questions along the way, but the first question is going to be, what's the efficiency? All right, how efficient is this engine? Well, this is one, since we were given the work, we can just jump straight to the definition. So we're going to take our work, we got 5,000 joules out of it, but we were requiring 20,000 joules to get that 5,000 joules. So that's 25%. So this engine is 25%, which is probably a little bit high. I think most actual like gas engines, it's more like 20% thermal efficiency, but we'll call it good. Okay, so there's our efficiency. So then how much heat do we lose? Well, it's just the difference, right? So let's just see. So the lost heat, well, that's going to be, oh, no, 12,000, 15. Right, so we lose the other 15,000. And I want you to see that this form would have worked out perfectly if we had wanted to use the other form. Think of this lost heat, that's our QC. The 20,000 was our QH. So 15,000 over 20,000, that's 75%. So then 1 minus that 75% is 25%. Okay, so we're losing this much. So now here's my next question, is how much gasoline are we burning? So if we just think about this as like one cycle of this engine or whatever, in order to get this 5,000 joules, how much gas do we actually have to burn? So let's think about this. What do you need to know in order to calculate that? And I'll leave this open to you guys. What do you think? What kind of number would you need to know in order to figure out how much gas gets burned?
The number of moles.
Okay, so if we had a number of moles of the gas, then if we knew the like molar density or something, that we
Yeah, like the concentration, the molarity.
Okay.
Yeah.
All right, so we could try to approach it that way. But that's a real like chemist way of doing it. Ugh.
Well, I mean,
physicists.
okay.
I'm just kidding.
A total amount of kinetic energy lost.
Okay, so think about kinetic energy loss. Kind of where you're going for is probably what's producing that heat, right?
Yeah.
Like if we could figure out what produces that heat, that'd be good.
Yeah.
So,
now that I think about it, maybe it's more gained because we're heat burning it. Might be gained. But yeah,
okay.
Where the heat's coming from.
Yeah. So where's that heat coming from? What's producing that 20,000 joules? All right. Well, let's think about what kind of process is happening. So when you are burning gas, what are you doing?
Are we combusting it or burning it?
Yeah, we're going to combust it.
Okay. We're increasing pressure and decreasing volume, which will change temperature.
Okay. And then we're going to get this change, right? So combustion is a chemical change, right? So it turns out I got to give you a new kind of number that you've never seen before. I'm going to give you an L sub C. So do you remember what L was? What that stands
Length?
for? Well, yeah, but in the thermodynamics world,
I don't remember.
we had an L sub F and an L sub V.
Latent heat.
Okay, good, Jacob. That's your latent heat. So this is the latent heat of combustion. So latent, remember, means hidden. So it's heat that's going in that's not causing a change in temperature, but causing a change in chemical state. And so that's what this is. This is how much heat do we need to put in to convert this gas from uncombusted gas to combusted gas. So let me just tell you that for gasoline, the latent heat of combustion is 5 times 10 to the 4th joules per gram. So if you want to combust 1 gram of gasoline, you would need 5 times 10 to the 4th joules. So in terms of the form for this equation, or to calculate how much is being burnt, we're going to have our Q, I'm going to call it QH, because that's what we're getting. It's going to equal mass times this latent heat. And this is exactly the same formula that we used for all of them, regardless of which latent heat it is. So the mass is going to be QH divided by that latent heat. Let's say this had been water that we're boiling, then we would use the latent heat of vaporization, but it'd be the same kind of idea. So we're going to take 20,000 joules, that's what we're shooting for, and we're going to divide by that 5 times 10 to the 4th joules per gram. Well, 2 times 10 to the 4th divided by 5 times 10 to the 4th is 0.4 grams. So in order to get 5,000 joules of work, we're having to burn 0.4 grams of gasoline.
That's way easier.
Than doing any
What
kind
I
of
was,
molar.
yeah.
Yeah. Yep. Sometimes it helps to get out of the weeds, right? Like when you're in chemistry, you're looking so closely at it that sometimes you forget to like pop back out and go, oh yeah, here's another approach. And just so you know, Bradley, that happens all the time with people that have taken chemistry before physics when we get to this kind of stuff. Because you are thinking like a chemistry student, which is fine, because that's where you've done this before. But sometimes if we can change our perspective to this bigger idea, like this is definitely more macroscopic, right? Big picture. Nowhere in here did we actually talk about what's specifically happening within those molecules to cause this stuff to combust and blah, 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 right? So getting out of that real detail can sometimes, well, it definitely makes it easier. So, all right. So there's just a quick example of how we deal with efficiency. And really, the biggest challenge is sometimes finding those cues, but you can find those cues using things like latent heat or specific heats or the like, if you know what's happening with that heat transfer. Are we changing phase or are we changing temperature? What is changing temperature? And so on, then you can calculate them that way. All right, so there's an example of doing this. But what I want to show you now is just an example of a cycle that happens when we, say, have a gasoline engine and it's going through its thing. All right, so I don't know how much you guys know about gasoline engines, like the engine in your car and what the process is, but let's talk a little bit about what happens. Okay, so this will be gas engine. And I'm going to put gasoline engine. Okay, because gasoline's not actually a gas, although in our engines it does tend to get vaporized before being put into the cylinder. But okay, so here's what goes on with a cylinder. So you've got a cylinder in your car, and in that cylinder is a piston. I'm going to put my piston on the bottom. It can just as easily be on the top. But let's just think about this piston. Okay, so that piston is just going to go up and down. And then up here, it's going to make a little thing. So what we're going to have is a spark plug. So that's going to be up there at the top. And then there are a couple of valves. There's an intake valve and an exhaust valve. And they are exactly what they sound like. The intake valve is the hole over which the stuff comes in. And the exhaust valve exhaust valve, that's the hole where things leave. Okay, so here's what happens in a gasoline engine. Here's kind of the process. So let's start it at, we're gonna bring gasoline in. So if we're in that stage, here's our cylinder. Our piston is going to be pretty much fully extended. And we're going to be opening the intake valve. So I'll actually show it as a opening like this. All right, so we open the valve, which lets the gas vapor mixture come in. So now that piston is going to extend down. So it's going to extend down. And now this container, this piston, is full of gas. So here's all the gas vapor that came in. Okay, so it works its way down because it just got full. So it gets full, and we now close this valve. So both valves are closed. All right, next, that gas gets compressed. That valve comes up here again, or sorry, that piston comes up here again. And now all of that gas is highly compressed. All right, so again, both valves are closed. And then it's at this point, a spark is produced. So the spark plug that sticks down, it just creates an electrical spark, which then causes the combustion. So there's an explosion. So all of this stuff gets combust. So think about what that wants to do. That creates incredible pressure, which pushes that piston back down. Okay, so now we're going to be in a picture that looks like this. Piston is down because it kind of got shoved back down. But now what we've got in here is fuel that's been combusted already. It's used fuel. So I'm going to make it kind of wavy, so it's like smoke. Okay, so then there's one more thing that happens. We now have that piston go back up, and we open up the valve over here. We open up that exhaust valve. So I'm going to draw this picture down here. So now there's the opening in the exhaust valve. We have our piston up high again. And all of the smoke has gone out. Okay, so this is the process. We'll follow the arrows. And then once all of that exhaust goes out, we close that valve, open up the intake valve, and repeat the process. Okay, so this is a cycle. It's actually called the Otto Cycle, but it's not Otto like you think, it's Otto like the person. So this is the Otto Cycle. All right, so this is the general cycle that happens when you've got a combustion engine going. Okay, so what I want to do is I want to look at each of these stages and try to draw it on a PV chart. So we can actually look at that cycle and think about how much work is done and all that good stuff. All right, so you remember your PV chart, hopefully. So we're going to have volume on the horizontal, pressure on the upper, right? And so let's just talk about what happens when we're at the different places. Okay, so we're going to have the gas enter at some volume pressure combination, but it's going to be at a lower volume because the volume in here is kind of on the small side. So we're going to have whatever our volume is and pressure, and the pressure is going to be very low, right? We're going to have very low pressure. And anyway, so we're going to be there. So let's choose a point. Let's say right here. Okay, so the gas air mixture enters. Actually, you know what? Let's do this. Let's do this. Let's be at this point in our cycle. All right, so I'm going to call this one A. That's where we are. So we have full tank, so big volume, low pressure. Okay, but then we compress it to a lower volume and a higher pressure. So that means we're going to be somewhere up here. Let's call that B. And on our way to B, there's going to be some work done because we have to move the piston, right? So the piston is doing work on this thing. So that means we're going to kind of follow, say, a curve that does something like this. All right, so this is going from A to B, basically. So now let's think about what's going to happen as we go from B to C. So there are actually two things that are going to occur here. The first is the change from unburnt fuel to combusted fuel. And then the second thing that has to happen is this change in volume. So we're actually going to have two little stages here. The first one is going to be a vertical line. So think about what the vertical line means here. That means there was no change in volume. So that's we burn the fuel, but we don't change the volume. But then we get the expansion. And the expansion is going to do something similar where we're going to get back to the same volume. But we're now going the other direction. And it's going to be a different pressure just because of the fact that we have different kinds of stuff in here, right? This intake fuel was just basically sucked in as opposed to this spent exhaust was created. So that's why it's at a greater pressure. Okay, so if I label these points, C and D, C is kind of in the middle, right? C is that we just burnt all the fuel. And then C to D is expanding that cylinder. Okay, so then what we do is we open the exhaust valve. So we decrease our volume, or sorry, we decrease the pressure because we shot out all that exhaust, and then we get back to here. So this is a straight line down. So this is what this cycle looks like. All right, so we, from D to A, we are expelling all the exhaust and in bringing in all of the unspent, or all the new fuel. From A to B, we're compressing the fuel. B to C is the boom. C to D is we're expanding the piston back out. And then again, D to A is expel exhaust and suck in new gas. And then it just continues going around and around and around. So let's just kind of digest this and think about what the 4 different pieces on here do. So the bit from C to D, this is where we're getting our power. It's sometimes called a power stroke. All right, but this is where the engine's actually doing its thing. This is why your car can go forward, is because of this step right here. The A to B, this is the compression. So sometimes they call that a compression stroke. And this is work that we have to do to get the other work out. And so if we're going to just talk about work, remember work is the volume, or sorry, the area underneath these curves. And so in terms of the work that we actually get, the net work is the area within this cycle. So we're getting more work from the power stroke than we're using for the compression. So there's our work. All right, now there has to be heat though, right? Because if we're going to do a cycle, like think about going from A back to A, we're back to where we started, and we saw that the change in internal energy there would be 0, which means there has to be some sort of a heat to balance that work. Well, here's where they happen. The QH, the heat that's being added from the heat reservoir, the hot reservoir, where does that happen in this stroke? Where are we actually producing the heat? I know you guys can figure this out. What part of this whole thing introduces heat? Makes fire go boom.
Oxygen.
Okay, well, it definitely needs oxygen, but there's something that actually causes the boom.
The C step, where it's all compressed upward.
It is. It's in that C step. What I'm looking for is spark plug. Right. That's the tool of the heat production. Is the spark plug. By putting in that spark, you're putting in heat that's converting this unspent fuel into combusted fuel. So the QH is entering right here. Well, we also know that this isn't going to be 100% efficient. So there has to be a loss of heat. So where in this stroke are we losing heat to the environment? And you can assume that this is really well insulated. Technically, we do have heat that's leaving otherwise. right? That's why like your engine gets really, really hot. But can you see the part of this cycle where we actually send heat to the environment?
Doesn't it just radiate off?
Well, there is that bit. But like I was saying, if this is like a perfect world where that doesn't happen, we're still sending heat out.
CO2, I'm sure it's really hot when it comes out.
Yeah, you're getting it. It's the exhaust. It's this part right here. When we open that exhaust valve and we blow out that exhaust, we're sending heat away. So the QC happens here. So in a typical gasoline engine, these are the thermodynamic processes. I guarantee you've never thought about this as you've driven your car down the road, and that's okay, I haven't either. But this is the cycle and what's going on. So let's see if we can calculate the efficiency. Let's see how good this ends up being.
Is this going to make me angry?
Potentially.
Okay.
I mean, I think the first time you see it, it does kind of make you mad. But then you realize that, well, you know, these things happen. It's just the cost of trying to mechanize this. Basically, what you learn when you take thermodynamics is that there's always a huge hit. No matter what you do, there's always a good amount of energy that's lost that you can't harvest. So, all right. So what we want to do is look at the works and look at the heats and just kind of do the math on this. All right. So let's start with the heats. So those are isochoric events, right? Same volume. Since they're isochoric, we know like QH, it's going to actually equal the number of moles times the constant volume specific heat, right? Because we're isochoric, times the change in temperature. So I'm going to call this TC minus TB to correspond to the numbers of the points, right? There's a certain temperature when we're at point B. I'm calling it TB. And there's a certain temperature here, TC. Okay, so then for the cold, again, it's going to be N times CV because we're expelling the same amount of gas that we took in, that we burned, right? So that is another assumption, is that we're expelling everything every time. So we've got that. But then again, we need to take our change in temperature. And in this case, we're going from D to A. So it's going to be TA minus TD, right? Ending point minus starting point. So just a real quick aside, we know that this one is positive, the QH is positive, and the QC is negative. All right, so let's look at efficiency. So the efficiency is going to be 1 minus And we're going to have the absolute value of the QC over the QH. So the NCVs are going to cancel. So we end up with 1 minus TD minus TA over TC minus TB. And before you yell at me, because I know you're about to, I did intentionally switch the TA and the TD. Do you see why? It's the absolute value. Since this is negative, absolute value has to change the sign. So I just flipped them over. So let me get a common denominator here. So this is going to be TC minus TB plus TA minus TD over TC minus TB. So really, we just need to know what those 4 temperatures are. If we can calculate those 4 temperatures, we can calculate our efficiency.
For this equation,
Yeah.
it doesn't matter what temperature scale we use.
We should always be on Kelvin,
Okay.
but no, yes, it always must be Kelvin.
Okay.
Calculating the differences, actually, no, you're going to be fine if you're in Celsius, because if you really think of it as the 3 difference pairs, I guess really 2 difference pairs because this one's the same one. Because whether you're in Kelvin or Celsius, your difference will be the same. I just recommend anytime you do thermodynamics, do things in Kelvin. Then you don't have to worry about it. But I think, Bradley, that, yeah, you can go ahead and get away with it without. Okay, well, we're going to take this a little bit further because this is great and all, but we don't always know temperatures. So what I'd rather do is see if I can turn it into other things that I do know, like volumes and things like that, because you'll know the volume of your cylinder, right? Those specifications are known. So you go and you look at your engine in your car, you'll know things like the volumes. You'll know things like compression ratios, like those are given. The temperatures that you're running at, who knows? Okay, so here's what we're going to do. We're going to assume that both of these strokes, both the power stroke and the compression stroke, are adiabatic processes. So adiabatic, do you remember what that means?
No heat transfer.
Good. So there's no heat transfer. And those tend to be ones that happen very quickly, right? And in an engine, these strokes happen very fast. So it's not a terrible assumption. So we're going to assume that these are adiabatic. But because they're adiabatic, we know that there are relationships between T and V and all that good stuff. Okay, so just to kind of remind you from what we saw before, when you have adiabatic, we created a whole series of equations, but one of them is that T times V to the gamma minus 1 is constant. So T is temperature, V is volume, and then gamma, I don't know if you remember what that was, but that's a ratio of the two molar specific heats, the constant volume and the constant pressure. And it's going to be depending on what kind of gas you have, monatomic versus diatomic versus polyatomic. All right, so it's a property of a gas. So let's just think about, say, the compression stroke. So we're at this bigger volume, we go to a smaller volume, and along the way we go different temperature. So we would get, say, TA times VA to the gamma minus 1. That's going to equal TB times VB to the gamma minus 1. So what this is going to let us do is relate TA and TB. And you can do a similar one on the stroke from C to D. So we'll have TC times VC to the gamma minus 1 equals TD times VD to the gamma minus 1. And I know you're looking at that and going, well, this doesn't really help because we're just going to trade temperatures for volumes, except for the fact that some of these volumes we know are the same. Which ones are equal? Which of the V's are equal to each other? It's this easy. Remember, volumes, vertical lines are same volume. So B and C have the same volume, as do A and D. So we know VA equals VD and VB equals VC. So instead of having 4 different temperatures, we can actually get it down to having 2 different volumes. Just smile and nod. Not that I can see any of you, but smile and nod. So we basically have cut the number of unknowns in half. That's awesome. But we can even go further because most engines have what we call a compression ratio. Okay, and that's just going to be R. And basically the compression ratio is telling you how much the volume changes. And so this would be the full volume over compressed volume. So I don't know if you remember, but we did this when we were talking about the burning of the paper. When we actually measured it, we saw that it went from a volume down to a volume that was like 1/11th it or something. That would be a compression ratio of 11. Full was 11 times as full as the smallest volume. Well, if we have that, then this tells us that the big volume, so we'll call it VA, is going to equal R times VB. We could similarly have said the volume of D as R times the volume of C, or whatever we want. Okay, well, if we add this into the mix, now we're down to just one volume. Like if we know, say, VB, we know VA. If we know VA, we know VD. And VB also tells us VC. So like if we knew that volume, the lower volume, we get all of them. If you know the full volume, VA, well, we get VD and VB. And then from VB, we get VC. So if we know the compression ratio, it turns out we only need to know one of the volumes. Okay, well, if we make use of that, we can change this efficiency into one that's in terms of volume and this compression ratio. I'm going to spare you the math. You can look at it in the book or kind of work it out yourself. But we end up getting 1 minus 1 over R to the gamma minus 1. So let me go ahead and put a box around that, because as always, that means we're done. But that's also what I want to look at. And so here is why we know that it's impossible to have an engine that's 100% efficient. Because think about what we would need for this to equal 1. For this to equal 1, the second fraction would have to equal 0. And it can never equal 0 because there's a 1 on top. Now, it's going to get better as R gets bigger.
Yeah, I was just about to say, what if R goes to infinity?
Okay, but remember what R is. It's the ratio of the volumes. So that R is going to be completely open piston
Yeah.
to completely closed. And so there's going to be a limitation how much, it's really going to be, like, I guess the biggest limitation would be the smallest volume, right, compared to the biggest. But it's never going to be, I mean, it can't be infinite. It's going to be a finite number. And there's going to be a limit on it, really, due to, just the engineering involved, right? But also realize that when we're talking about this, we're talking about something that's completely insulated, that there is no heat loss otherwise. And I think this is about when it starts angering Bradley, because this is best case. Best case, perfect world engine. So even in the best case, where we're not losing heat due to anything else, this is our best case.
That sucks.
Yeah. Yeah, it does. There's a limitation. But think about what's going to make it better. Well, first of all, gamma is pretty much fixed, right? It depends on what our not our gasoline, but our gas looks like. For air, remember it's around 1.4 or something like that. So that's usually fixed. Your air-gas mixture in your piston is going to have a set gamma. And it really doesn't matter what kind of engine you have. As long as it's a gasoline engine, that gamma is going to be the same, because gamma is a property of the gas-air combination. You have like a diesel engine, that's a different story. But that gamma is fixed, which means the only thing we can affect is R. So what you'd want to do is be able to increase your R in such a way that we get decent efficiency. But there is a little bit of an issue with that. If R gets too big, So we're compressing it down really far. Sometimes you can get combustion to happen before you want it to. Like go back to that idea of the paper, when I had the paper in the plunger and I shot it down. It caught fire when the temperature increased to a high enough point, which might have been, like in a gas engine, might be before the spark plug goes. And you don't really want that to happen, right? So there's also a limitation there, that if your compression ratio is too great, you'll increase your temperature too much, and you'll get a premature combustion. Anyway, so you can kind of play around with different numbers. I ran one with a gamma of 1.4, and if R is 8, let's say you've got a piston that you can compress down to 1/8 the volume, this efficiency ends up being 56%. So even if you're able to compress it down to 1/8 its volume, best case scenario is 56% efficiency.
That's wild.
Yeah. And this has nothing to do with our ability to construct, our ability to insulate, our ability to create new materials, none of that. This has everything to do with what we're burning, and even that, the gamma can't change much. And then just your compression ratio. So it's this kind of limitation that led to the second law of thermodynamics. Before we get there, I want to show you what happens with like a refrigerator or an air conditioner or something like that. Because you'll see that we have a similar issue if we're trying to cool something. Right? This one, we're trying to use heat to do work. The other way, we're trying to do work to cool things down, basically. But I want to show you that we get a similar issue. I don't want to talk about a diesel, because it's really kind of the same idea, but for a diesel engine, it works a little bit different, because it's the change in volume. There's a compression that leads to ignition. There's not a spark plug. It's you use the compression to change the temperature, which then makes the fuel go boom. So because it's a different thing, it looks a little bit different. You end up with flat on the top and bottom. You have some constant pressure things with change in volume. But other than that, it kind of does the same thing. But let's talk refrigerators. Actually, before we do that, let's take a break. This is a good place to stop. So I'm going to hit pause. Okay, so now that we've seen how heat engines work and how there is a limitation to the efficiency, let's go take a look at refrigerators, or if not a refrigerator, an air conditioner, or anything else that's trying to keep something cooler than the outside world. Okay, and we'll see how it relates to what we're talking about and how we can do kind of a similar approach. And we'll see that there's definitely a limitation there as well. So I'm going to go back to the whiteboard. All right, so let's look at a refrigerator. So in terms of the cold reservoir and the hot reservoir, the cold, this is our refrigerator. Okay, that's the inside of our fridge. So it's keeping a colder temperature, and let's just say that it's at a temperature T sub C. Be really creative here. Temperature sub cold. Okay, now the outside world is up here. And when I say outside, I don't necessarily mean literally outside my house. I mean outside the refrigerator. So This is just the air in your kitchen, let's say. And it's going to be at a temperature, let's call it T sub H. Okay, so what has to happen now is we're going to have heat being removed from the refrigerator. Right? The fridge is trying to cool off. Well, we're trying to cool it off. It's actually trying to warm up because of thermal equilibrium stuff, right? So it's trying to warm up. So we need to remove heat. Now, to remove the heat, we are going to do work. So if you look at this picture, it's kind of similar to what we had before, except the arrows are pointing in the opposite direction. So we're going to have heat that's leaving the refrigerator. So we'll have QC. We're going to have heat that's entering the outside world. And we're also going to be doing some work. So we can kind of set this up exactly the same way, where we see that the heat that's entering the hot, so QH, and again, let's go absolute values. That quantity, that's going to equal the work plus the heat that's being removed from the cold. And I'm going to go ahead and throw absolute values around that as well. But let's talk a little bit about plus and minus. QH is going to be minus because heat is going into the hot when what it really wants to do is leave the hot. Right? So that's actually going to be a minus. That's why the absolute values around that are supremely important. But we can always just put absolute values around all these. And actually, if we were just to do this one covers both a refrigerator and a heat engine. So I'm going to write that here. So this works for a fridge or a heat engine. So this is the one that I like to remember, just because it makes life easy. You do sometimes have to pay attention to plus or minus which direction they're flowing, but that's just easiest to do. All right, so let's look at how good a fridge is. Now, efficiency isn't the right word, really, because efficiency is suggesting that we're getting something out of our heat, but that's not what's going on here, right? We're actually trying to control the heat, and we're controlling the heat by doing work. So what we're going to do is create what's called a coefficient of performance. So it's going to be K. Now, the way we're going to define this is similar, except now what we want to do is we want to look at how much heat did we remove compared to how much work we put in. So if we were able to get as much heat removed as work we're putting in, then we'd have a 100% coefficient of performance. All right, well, if we use this relationship between work and the Q's and all that, we can get a similar formula that involves just the heats. So this should look really familiar because it's like the same thing we had before. It's just upside down. Okay, so here's your coefficient of performance. Now I want you to notice something about this. Like, what would make this better? What would increase this number? What makes a fraction bigger?
Either a fraction underneath.
Okay, so if we change top and bottom, like we could change the top by increasing that, but that's kind of hard, right? Like we're going to remove more heat. Well, the other way you could think about making this better is if the QH minus QC got closer. But that would basically mean that there's sort of like a free transfer of heat from one to the other, which means they're kind of in thermal equilibrium, which they're not going to be. I mean, your refrigerator is going to be much more or have a higher coefficient of performance if, say, the outside world was 35 degrees and you're trying to keep the refrigerator at 34 degrees. Right, so that's kind of a, yeah, well, duh. But I just want you to notice that there's a limitation here. Just like before, it's different, but the limitation really is this guy right here, the QH minus QC, and those are going to be dependent on the temperatures inside and outside. All right, so think about your refrigerator. Where does it release the heat? Do you know? Have you ever even thought about that?
I think it's out the back, isn't it?
It is out the back. There's usually a whole big series of coils. And these coils, usually we use Freon, but it can be some other kind of gas. But it basically sends that gas into the refrigerator, comes back out, releases that heat into the outside world, and then goes back in and just completes the cycle. So if you can access the back of your fridge easily, you can see, and if not see, because it might be covered, you can feel the heat. Air conditioners do the same thing. Like if you've got a window air conditioner, it's got that part that's sticking outside, and that's where it's sending the heat. Similarly, it's passing some sort of a gas through it. Sometimes it's water, but those we usually call heat pumps, but it's the same kind of idea. And so it's releasing the heat outside. If you've got a whole house air conditioner, or if you've ever been in a building with an air conditioner or air conditioning, there's usually some big machine outside on the roof or something that releases it. So refrigerators, air conditioners use this. Heat pumps are slightly different. Heat pumps are kind of crazy that they actually cool the outside air, but then they're drawing hot air from inside your house. It's the same kind of idea. But anyway, so similar idea, it's just not, instead of efficiency, we flip it over and it's coefficient of performance. All right, well, this is what led to the second law of thermodynamics, things like these. So let me give you the second law. All right, so what the second law says, and there are a bunch of different forms. So let me give you the first one. And the first one just says, heat cannot independently move from a cold reservoir, maybe independently, spontaneously, maybe better, spontaneously, move from a cold reservoir to a hot reservoir. Okay, so this is one form. I'll show you some other forms in a second. So basically this says that heat transfer is one way. You can only take heat from a warmer source, so a higher temperature source, and give it to a colder temperature source. If you want to go the other way, you have to do work. So this is the version that's kind of related to cooling, to refrigerators, to air conditioners, right? Like if you want to make ice, you have to do work to make that ice happen. Well, it's your refrigerator, your freezer, right? There's enough power being supplied to remove heat from an already colder source. Since Bradley brought it up earlier, in Back to the Future 3, don't know if you've seen that one. That's the one where they go back to the Old West. And there's a scene where you see this huge contraption that Doc has built. And, you know, there's steam going, whistles blowing, blah, blah, blah. And then finally a little thing opens up and an ice cube falls out. Right, so he's making ice. But it takes this huge contraption. Well, that's this. It requires work to be done. So at least in that aspect, Back to the Future got their physics right. So we'll give them a thumbs up for that.
Yeah, I'll watch that one later tonight.
Yeah, and you'll know exactly what I'm talking about when you see it.
Okay.
And you'll go, ooh, second law of thermodynamics. All right, so this is the like refrigerator form. But let me give you kind of the heat engine form. All right, and what that says is that it's impossible to convert all heat into mechanical energy. So that's there's no such thing as a perfectly efficient engine. So you kind of got a refrigerator form and an engine form. So there's always going to be some sort of a loss of energy. And like I said, it has nothing at all to do with our ability to construct stuff. It's entirely due to the limitations of the laws of physics. So this second one, is what eliminates a perpetual motion machine. So I don't know if you've ever heard of a perpetual motion machine, but this would be a machine that produces more energy than it uses. And every once in a while, you'll get a crank physicist. I'm using that term as, you know, the standard usage of someone who's kind of fringe and isn't doing things quite right. But you'll get a physicist who says, or an engineer is like, oh, I've got this machine that gives me more energy than I put into it. Unless the laws of physics have changed, or there's some bit of it that we don't understand, it's not possible. That doesn't happen. So it's impossible to have a perpetual motion machine. Now, that doesn't mean that in movies and stuff they don't do that all the time, but that's definitely a really big stretch, which is often hard for me to ignore, but sometimes I'll let it go. Like, I don't know if you guys have ever seen the movie Snowpiercer. There's is it TBS maybe has made a new show, TNT, one of those, has made a TV show based on it. It was a few years ago. But the idea there is that it's end of the world and there's a train and all the people that still live on Earth live on this train, but it has to keep in motion because its motion is what's powering the train. So it's basically a perpetual engine machine, perpetual machine. And I've been able to overlook that because I like that movie. It's kind of a good one. It's got Chris Evans. But definitely the physicist in me goes, ooh, no. But I have to do that all the time with science fiction movies anyway. It's a little bit easier to make it okay in like a fantasy movie because fantasy movies, as soon as you allow for like magic, well, then all bets are off. All right. So with this said, the question now is, what's the best case scenario? I mean, we saw what the best case scenario was for a gasoline engine and all that. But what if we just want to go to generic? What is the best, most optimal way to get the most bang for your buck? All right, so there was a French physicist by the name of Carnot who thought about this and reasoned what the cycle should look like for best case scenario. Okay, so this is going to be the optimal situation. So it's called the Carnot cycle, named for him. So it's Carnot, but he's French, so he's Carnot. Okay, so this is what he said. This is how he kind of reasoned it. So first, let's just say that we've got a container of gas, and we're going to do the whole piston thing. This time I'm going to put the piston on top, just because that's usually how we like to think about these. Just car engines, the pistons are on the bottom. Okay, so let's say that we're here. So thinking about what would be best, he said, let's start by compressing isothermically. Okay, so step one is going to be isothermic compression. So we know what compression means, and isothermic means same temperature. So we're keeping the same temperature. We're just compressing it a bit. So at this point, what we're doing is we're sending out heat. Okay, so this is what's going to be going on. We're going to be sending out heat. And you might be saying to yourself, but wait, Bruce, you just said this is isothermic, so that the temperature doesn't change. That is what I said, but remember, temperature is not heat. Heat is different. We're sending out heat because it's countering the work. Remember, in isothermic means the change in energy equals 0. Because if the temperature is the same, there's no change in internal energy. So by the first law, Q is going to equal W. Okay, so Q equals W. And there's definitely work that's happening because we're compressing the gas. Since we're compressing the gas, that's negative work, which means we need to have negative Q, which means we're sending out Q. All right, so that's going to be stage one. We're going to do an isothermic compression. All right, then we're going to continue compressing, but this time we're going to do an adiabatic compression. So in this picture, our piston is now even further down. So we're still compressing, but we're doing it adiabatically. So again, what does that mean? What's adiabatic mean? So adiabatic means Q equals 0. There's no heat. So all the work that's happening is changing the temperature. Okay, so then the next stage is going to be an isothermic expansion. So we're really making use of the same thing where there is no change in energy. So that means that all of the work comes from the heat. So basically at this point, we're absorbing heat. So this is the stage where we have to absorb heat. So we're absorbing heat after we had already lost our heat. Okay, so we're expanding. So let's bring this guy up a bit. And then the last stage is to do another adiabatic expansion. So Carnot reasoned that looking at this, or looking at all the different possibilities, that this is what's going to maximize your return. All right, so your best case is to do this alternating isothermic and adiabatic bit. All right, so let's look at best case. Let's look at this best case and see what our efficiency would be. All right, well, basically we need then to look at what the work is and see how that work compares to the heat. All right, well, let's start with QH and QC. So those things are happening with isothermal expansion. So I don't know if you remember, but we did calculate work done during an isothermal expansion. And so QH, isothermic, it ends up being nRT times the natural log of the ratio of the volumes. Okay, so let's call this V final over V initial. Okay, so this is in general what it would be. So the temperature, let's just call that, say, TH. And we'll go ahead and leave those as V initial and V final. And then similarly, we'll have a QC, which does the same thing. Actually, let me change them, because let's label them, and let's label them as such. Well, it doesn't really matter where we are. Let's call this one, this volume A. Call this one volume B, this one volume C, and this one volume D. So those are the different volumes we get after these different expansions and stuff like that. So the Q hot, we're going from VC to VD. So that means that this is going to be VD over VC. And then for the cold heat, that natural log, we're going from volume A to volume B. So that's going to be VB over VA. All right. Now, it does turn out, though, that the QC is negative. I'm going to put a minus sign on that because we're losing heat, right? It's heat that's being removed. So what I really want to do is I want to look at the ratio of those, because it's the ratio of those that give me efficiency. Remember, it's 1 minus that. So let's look at QH over QC. And specifically, let's look at the absolute values of those. So the N's are going to cancel, the R's are going to cancel. We're going to get TH over TC. And then we're going to have these natural logs. So natural log of VD over VC divided by the natural log of VB over VA. And we'll throw those in absolute values for right now. Okay, now, to help us at this point, we're going to use the adiabaticness. So remember with adiabatic, we just used this a little bit ago. We know that T times V to the gamma 1 is constant. And so in those two adiabatic expansions, the temperatures are either hot or cold. The cold temperature, we got the VB and the VA. So we could have TC VB to the gamma minus 1 equals TC VA to the gamma minus 1. And then similarly, we can do for the hot, we have TH VA gamma minus 1 equals TH, no, not VA, VC, all right. TC VD gamma to minus 1. TH, yeah. So from this, we find out that VB over VA is actually the same as VC over VD. And so if those ratios are the same, I got something backwards because they're supposed to be exactly equal. Oh, no, actually, it doesn't matter. I think I'm okay. So since they're the same, their natural logs are just off by potentially a sign, which means when we take the absolute value, this equals
Always
1.
is 1. Yeah.
So,
It's just the
once,
temperature difference then?
yeah, so once all is said and done,
That makes sense because you're looking at the constant.
yeah, it's because of the isothermal and adiabatic. Like, this is why this is the best. It's because it just, like, everything else sort of plays out.
Yeah.
Okay, so we see that the ratio of the heats is actually equal to the ratio of the temperatures. So then if we go to efficiency, I actually had these backwards. It's supposed to be the other way around, right? It's 1 minus QC over QH, which is going to equal, oh, and these are both positive, so you can drop the absolute values, right? If we're on the Kelvin scale, those
Yeah.
numbers have to be positive. So this is 1 minus TH over TC. No, reversed it again. Okay. TC over TH. So this is TH minus TC over TH.
Yeah.
So let's put a box around that, because that is absolutely best case efficiency. All right. So notice that this has to be under 1. Because what would have to happen for this to equal 1?
The TH and TC are the exact same? Or no, that'd be
Nope,
0.
not quite. If TH and TC are the exact same, then you get
That's
0.
It would be, TC is 0. Would work.
Okay, and that's it. You'd need
Which is
TC
an
to be
impossible
0
though, right? In Kelvin,
in Kelvin.
for all that we know.
So 0 Kelvin is a theoretical, but can't happen because then matter breaks down.
And that's why we can't have perfect efficiency,
Exactly.
mathematically.
So because of the nature of temperature and what 0 Kelvin means, and how everything else is based off of this Kelvin scale, like we've just been adding more pieces to the puzzle, right? We just keep putting them together, and it led us to this picture, which this is, again, probably a picture Bradley doesn't like to see, because it tells us that there's a limit to the efficiency. And this is best case. This is absolutely best case.
Well, and that's the question is it only based upon in heat or in temperature? Can you have other almost more effective energy methods? Or is temperature like intrinsic? It's just intrinsic in general because that's just like the basic measurement of atomic movement, I guess, right?
Yeah. Well, it turns out that this is the best. That any
Okay.
other combination
It's just
of
not as efficient.
processes will drop your efficiency even further. And so I think it does kind of make sense that the best efficiency comes from somewhere where it's based only on temperature, because like you were saying, Ian, that's sort of like the measurement of what's going on.
Yeah.
And so it makes sense to me that if we're going to look at, optimum or optimal, it would be when these things, or when we can do that, when we can look at it just with temperature. So best case, but obviously just about everything else is not best case. So let's just think about this. Let's think about the refrigerator that's in your house right now. All right, so your refrigerator is probably set at just a couple of degrees C.
Yeah.
just slightly more than freezing. So let's just say 5. That might be a little bit on the high side, but let's go with 5 degrees C. And then let's just go with a good old room temp on the outside that's, not crazy. Let's go 25. So on a summer day, if you don't have air conditioning, that's probably reasonable.
Mm-hmm.
So let's look at what the best case efficiency would be. So if your refrigerator was actually working on a
That's
Carnot
just
cycle,
20 over
let's see what
25.
okay, so our efficiency E, we need the difference in these, which is going to be 20 over the heat reservoir, the hot reservoir's temperature. But remember, it's not 25.
Okay, so it's
This
the
is in Kelvin. So this is going to be 298.
Yeah. Not that efficient, but
No, not at
not
all.
efficient at all, really.
No. You take 20 and you divide it by 298. That's roughly 1/15,
Yeah.
right? I don't know. Where's my calculator? Let's actually get it.
This is a hard pill for me to swallow. It really is. It's bothering the hell out of me. It sucks.
That no matter what you do, that's like 6.7. So that's best case scenario. So, yeah, it's rough, right? Like, there is a limit on how good things can be, but this would be your best possibility. So there's a cost for us to have cold food.
Yeah.
For me to have my ice cold root beer.
We have to expend a lot of energy.
We do.
But that's like, I guess effectively we're screwed with just efficiency based off of the rules of the universe. So we need better power sources so we can just keep going on.
Yep.
I need my cold root beers every day.
Your cold root beers. Right. So, this is this isn't exactly how we want to do a fridge, because this was an engine, right? So a Carnot refrigerator would be going backwards. So it would actually be the reciprocal of this. So, and I'm sorry, I kind of didn't catch this for you. So this would be for an engine. And then for the fridge, if we're going to go backwards, again, on the bottom is going to be your TH minus TC. And then on top, it's actually TC. So this will make you feel a little bit better.
So 298 divided by the 20.
Okay, so again, this isn't an efficiency. This is a constant. It's a constant or coefficient of performance. So in this case, this would be 278 over 20, which would be 13.9.
So something, I guess a quick question is like, I guess more like in Diffie Q, but can you insulate the cold to closen that, or is it just like stuck the way it is?
So this is perfectly insulated.
Okay, it already is. Okay.
Yep.
Okay.
So the way to interpret this number the 13.9 is that's how much this is the number of joules that you remove for every joule of work done. Okay, so like in this situation, a perfect Carnot refrigerator, every joule of work you do is going to remove 14 joules of heat. So the bigger this number, the better. 13.9 is not bad. It gets better as these temperatures get closer together, right? Because that denominator drops. But honestly, a lot of the things that we do are even bigger temperature differentials, right? But also think about how many joules you need to remove in order to change the temperature, right? Like, let's just say it's only air in there. You'd have to take the volume of air and then use your molar specific heat thing. And you're going to find that it requires a lot to change the temperature.
Yeah.
Come back to my ice cold root beer, since it's mostly water, that's got a really high specific heat, right? 1 gram, to change the temperature of 1 gram of water, 1 degree C is 4 joules. So this 13.9, doing 1 joule of work would only allow me to cool 4 grams of water, 1 degree C. There's way more than 4 grams of water in here,
Oh yeah.
right? So basically the moral of the story here is we're screwed by the universe, by the laws of physics. There's only so much we can do.
Call them BS. We'll figure it out.
Okay, well, please go ahead, try.
I will.
And I think what it's going to come down to is we have to find something that where there's like an exception, or maybe not an exception, but I kind of think of this like relativity. Or quantum mechanics. Like Newtonian physics works really well. When I want to describe this pen dropping, Newton does a great job. But when I start looking at really high speeds, when I start looking microscopically, right, Newton stuff doesn't work so well. So we developed some new ideas that still generalize to Newtonian when we go big picture, and everything's fine. Well, there could be the big leap with thermodynamics, where there's something we don't know, or we don't see the whole picture, that we're just seeing sort of like the really far away picture. But as we walk closer, we start seeing, oh no, it's made up a whole bunch of different dots. By the way, I love pointillism. I think it's one of the coolest ways of making paintings. But okay, so maybe we haven't gotten close enough to see those dots. And that's where the revolution is going to come when it comes to thermodynamics, is if there is we can look close enough at it to see the detail that allows us to, kind of wiggle. Because we had huge advances because of that with quantum. Like, even if you just look at like our ability to make things smaller, right? Like think about the computer that's in your pocket right now, and think about the computer that had the equivalent computing process in 1960.
True.
Right? Not even close to fitting in your pocket.
Looks
It wouldn't
like
fit
the
it wouldn't
efficient
fit in my house.
of really large gravitational bodies. Like how efficient are say like the revolution around a sun, or say a black hole, for instance?
Efficiency is not the right word.
That's sort of like,
Because-
is it just its own form of energy that doesn't, like, I'm
So,
trying to,
so this, what we're talking about when we're talking about efficiency, and this is heat efficiency. There are different kinds of
have,
efficiency.
like gravitational efficient engines instead?
No, because we're bound by conservation of energy.
Oh, true. Yeah.
So something like that, we can even go to the bigger, conservation of energy kind of idea that limits that. So talking about like the efficiency of a planet in orbit doesn't really make sense,
Yeah, that's
right? But I kind of see where you're going with this idea, Ian. But there we're bound by the conservation of
constructive
energy.
Yeah.
And really, if you think about what we're doing here with all this heat efficiency, it's still conservation of energy. It's just a specific kind.
So more like how effective is the sun at creating those atoms?
Okay, so that we can definitely talk about, like
No.
what kind of energy return the sun gets.
For creating, spitting
Yeah.
out those.
So
'Cause-
that we could definitely talk about.
Those last very long, right? Suns last forever, right? Or not forever,
Well, yeah, not forever, but a
but
long
they're very
time.
efficient.
Our sun will eventually burn out,
Yeah.
right? It will eventually expend all its fuel. But yeah, nuclear processes are very efficient.
That's my only guess is black holes. But that's like, is that anti-efficiency? Like, I have no clue.
Well, if you ever
Tough
figure out
one.
what's going on in a black hole, you let me know.
Time
it-
changes.
And if it turns out that you're like behind some 4-dimensional bookshelf that lives in a 3-dimensional world, and you're trying to communicate to me through like the second hand of
just
a pocket
watched
watch.
that movie yesterday.
If
I
that
fucking
is
love
what
that
ends
movie.
up, please don't tell me, because I don't want that to be what's inside of a black hole.
Oh no.
Okay, so
Fair enough.
just humor me and make something up. Tell me it's a dragon.
Perfectly efficient engine.
Yeah,
we
right.
made it. It's behind the black hole.
Just look at the books. It
I'll make
spells
sure
it
not to
out.
mention the bookshelf.
Yeah, right.
Hmm.
Anyway. Okay, well, I think we're going to pause here. We'll stop here for the day. So let me pause the recording.